or other things we'll do along the route of this tape. So, this particular lesson is going to deal with how to factor, some very simple classes of factoring techniques. We'll first look at a technique that's useful as your first step, and then we'll step back and look at the polynomial that we have left and analyze it to see which type of factoring it might be. It turns out, if we do it in this analytical fashion, it makes factoring a lot easier. So let's take a look at our first polynomial. Our first visual here, we have a polynomial with two variables in it. Most of the polynomials you will see in this tape series do not have more than one variable, for a very good reason. I think it's easier that way, and the application comes through very clearly. But just so it would look familiar to you, I thought here we'd use two variables, x and y. Now, the very first thing you always want to do when you are in a situation where you need to factor is what's called factoring out the common monomial factor. That is finding some monomial, some number or a letter or number times a letter or number times a letter times another letter that divides evenly into each and every term in your polynomial. It must divide evenly into each. So, we look at 6x cubed y squared minus 15x squared y cubed plus 9x to the fourth y. And the first question you ask yourself is, what's the largest number that divides into those coefficients? The answer is 3, because 6, 15, and 9 are divisible by 3. So we write a 3 down. Then we say, what's the lowest power of x in all those terms? And first of all, we notice that there is a power of x in each and every term. If, for example, the last term was 9y, it had no x in it, we could not factor out a power of x. So we see that each term has an x. What's the lowest power of x that's available? And of course, it's x squared in the second term. That means each and every one of those three terms can be divided by x squared. We couldn't divide by x cubed because we couldn't divide x cubed into x squared. That would be like dividing 1,000 into 100. Look at the y's. There is a y in each term. What's the lowest power of y? Well, in the third term we have a y, or y to the 1 if you want to be official. So we can factor out x squared y. So our common monomial factor is 3x squared y. Now we ask ourselves the question, what is the second factor? What do I need to multiply 3x squared y by to get the original? If we look at the next visual, we'll see that. I'm not going to spend the time going through each step. You need to go back and look at your multiplication, lesson 2, but you'll see it's fairly clear. We multiply the number times the number, the x times the x, the y times the y, and we get 3x squared y times 2xy minus 5y squared plus 3x squared. Notice again, the second polynomial is in parentheses. Why? We're showing multiplication. Can we check this? Yes, we can. Would it be reasonable to put an x in for a 10 in for x and a 10 in for y? It could. You could do that. Actually, with the two variables, I'd like to put in different numbers. So perhaps we could put a 2 in for x and a 5 in for y, or a 2 in for x and a 3 in for y, and check. But basically, that's the common monomial factor. And it should be the very first thing you look for anytime you factor. Now, what we're going to look at now is we look at 3 different situations. The first situation is when the polynomial that we need to factor is a binomial, 2 terms. The second situation will be when it's a trinomial, 3 terms. And finally, we'll look at what's sometimes called a tetranomial, or 4 terms. And we'll see what type of factoring will work in each of those situations. But again, I must remind you, the first thing you always do is look for the common factor. You look at these, whether it has 2, 3, or 4 terms, after you've either factored out the common factor or said, as we used to say in my old neighborhood, there ain't no common factor, or perhaps in your neighborhood, there is no common factor. Okay, let's take a look at the next visual. which is a multiplication problem. In fact, it's the exact multiplication problem we looked at when we were looking at multiplication patterns, and we saw that we have x plus 4 and x minus 4, that the plus 4 times x and the negative 4 times x cancels out, leaving us with a binomial. And therefore, we can say, wait a second now, we multiplied x times x and got x squared, 4 times 4 and got 16, x squared minus 16. Both terms in that binomial are squares. They were obtained by multiplying something by itself. X times x, 4 times 4. The reason for the minus in between the x squared and the 16 is because we had a plus 4 and a minus 4. Now, what that says is that if we have a binomial that is the difference between two squares, that is, the first monomial is a square term, and the second monomial is also a square term, we now have a pattern of factoring. So let's take a look at the next visual. Here we're given x to the 4th minus 49 to factor. X to the 4th is a square number because x squared times x squared is x to the 4th. 49 is 7 squared. So we have the difference, the subtraction in between, of two squares. And the factoring pattern tells us it's the square root, if you would, of x to the 4th. X squared plus the square root of 49, x squared plus 7 times x squared minus 7. The difference of two squares. Now what if we had x to the 4th minus 81? X to the 4th minus 81 is also the difference between two squares. And when you factor that, you get x squared plus 9 and x squared minus 9, since x squared times x squared is x fourth, and 9 times 9 is 81. But if you stop there on one of my tests, you would be in a problematical situation because you hadn't finished the problem. You always must look to see if you can factor further. And you'll notice that x squared minus 9, which is in the second parentheses in our visual, is also a difference between two squares. And we can factor that, x plus 3 times x minus 3, giving us our final answer of x squared plus 9 times x squared, let me go back over that, x squared plus 9 times x plus 3 times x minus 3. And if you wanted to plug in 10 to the original problem, x to the 4th, 10 to the 4th is 10,000. 10,000 minus 81, which is what, 9,919. You would get that by multiplying 109 times 13 times 7. Again, any one of these problems involving polynomials, you can check plugging in 10 for x. Okay. Let's take a look at the next visual. The next visual shows 5x cubed minus 45x. You say, wait a second, that doesn't look like the difference between two squares. And you're absolutely right. But you're also absolutely wrong. Because the first thing I said you should do is look to see if there's a common monomial. Then you look for these other patterns. And you'll notice that there's a 5 and a 45, which means we can factor out of 5, since both are in the 5 times table. And there is an x in each term. The lowest power, of course, is x to the 1, so we can factor out of 5x. And if we do that, as we'll see in the next visual, we get 5x times x squared minus 9. And the x squared minus 9 in parentheses, that indeed is the difference between two squares. And we wind up with 5x times x plus 3 times x minus 3. So that's the difference between two squares. You've seen a few examples of that. We'll come back and see an interesting example in a little while. Look at the next visual, which is back to multiplication. And there's a reason I'm showing you this problem. When you multiply x minus 3 times x squared plus 3x plus 9, you'll notice some very interesting things happen. You get x cubed, you get plus 3x squared and plus 9x, minus 3x squared and minus 9x, and negative 27. The x and x squared terms cancel out, and what you're left with is x cubed minus 27, the difference between two cubes. cube, of course, is a number raised to the third power. So x cubed is a cube, and 27 is 3 cubed. Look at the pattern of multiplication. X cubed minus 3 cubed gave us, working backwards, x minus 3, x squared plus 3 times x, and plus 9, which is 3 squared. So once again, you go to the board here and work this problem backwards. We had x cubed minus 27. That was the answer we got when we multiplied. Now we want to work backwards. I say there's no common factor because there's no x here and no number in front of the x cubed. It is the difference between two cubes. This is x cubed. This is 3 cubed. The sign is the same. Then I take the x squared, opposite sign, 3 times x, always a positive at the end because a negative times a positive is going to give us a negative, and I take the 3 and square it. That's the pattern. If it's not something you've seen before, rewind the tape, go back to the multiplication sequence, and see where I obtained this. Okay? Let's take a look at the next visual. The next visual says x cubed minus 125. Notice there's no